I'd like to welcome everyone to our seminar today. We're pleased to have David Ricketts from Carnegie Mellon here to speak to us today. And Hamid allowed me to take over the honors of introducing him since David and I have worked and taught together. And so it's my pleasure to be able to introduce him to you. David received his PhD from Harvard. He's an assistant professor of ECE and also has an affiliate or courtesy appointment in material science and engineering at Carnegie Mellon. And before coming to Carnegie Mellon, he spent 8 years in industry where he developed over 40 integrated circuits and mixed signal RF and power management applications. His research crosses the fields of device physics, material science, and circuit design, and his work has appeared in Nature, Proceedings of the IEEE, and numerous other IEEE conferences and journals. He's authored 2 books, Electrical Solitons, Theory, Design, and Applications, and The Designer's Guide to Jitter and Ring Oscillators. He's the recipient of an NSF Career Award, the DARPA Young Faculty Award, and the George Talman Ladd Research Award at Carnegie Mellon. In addition to his technical research, Professor Ricketts investigates the role of the scientist and engineer in creating breakthrough innovations and has co-developed several courses on innovation and creativity at Harvard and Carnegie Mellon. He's currently a Harvard Innovation Fellow in the School of Engineering and Applied Science at Harvard University and was a winner of the 2009 Wimmer Teaching Fellow at Carnegie Mellon. So it's my pleasure to introduce David Ricketts to you, and he'll be talking about the boundaries of high-frequency analog and RFIC.
Right.
Thanks, David.
Thank you, Dan. All right. Thank you for the introduction. This is a graphic overview of some of the work that my group does. We do work in analog and RF circuits, nanoscale devices, and some interdisciplinary systems work. Today I'm going to focus on 2 specific areas. The first one is on some work we're doing in millimeter wave power amplifiers, and the second area is in high-speed analog-to-digital converters. So the first part of my talk is going to be about speed and energy. This is looking at 45 gigahertz 4-watt power amplifiers. So the motivation of this work is we're looking at developing systems that can efficiently generate phase and amplitude modulated signals for communications. And it turns out one of the biggest problems is the power amplifiers operate most efficiently at a single supply voltage. And if we want to create an amplitude modulated signal using a constant amplitude PA, we need to do a few tricks. And one of the standard tricks is to use a phase modulation technique where we basically take the signal we'd like to create, we split it up into 2 parallel paths where we have a constant amplitude phase modulated signals, and we add these 2 together to produce an output waveform that looks something like this. And the way to think about this is if we have 2 sinusoids, if they're in phase and we add them, we get twice the amplitude. If they're out of phase, we get 0, and thereby with a phase shift, we can get almost any amplitude we want at the output. One of the challenges, though, is in this addition and also in combining power from multiple PAs, and I'll talk about that, both these areas in this talk. All right, so this is a plot some of you may have seen before. It plots power added efficiency, which I'll define shortly, versus frequency. Everything in the blue and the green are standard silicon, and then we have a few other technologies out there. And what you can see is there's sort of this barrier at about 20% power added efficiency from down around 20 gigahertz all the way out into the sub-terahertz regime. And so the goal of this work is to see, specifically at 45 gigahertz, what we can do to increase this and also deliver very high power. You might ask, why 45 gigahertz? Well, 45 gigahertz was actually mandated by our research sponsor. It's a stepping stone towards 100 and 150 gigahertz. So it's chosen more for a demonstration than for specific application. So I want to do a brief review of power amplifiers, because all of you may not have brushed up on this before the talk. This is a picture of a Class A amplifier. We've got a bipolar transistor in this case here. We've got a choke. We've got a DC coupling capacitor. And the way this works in the Class A is we're going to bias this transistor so that it's always on. So as the input signal goes up and down, the transistor turns more on, less on, and we end up with a sinusoid modulation of the output here. So you can see the drain voltage, or the collector voltage here moving around, and here's the current. Now, the efficiency of this is really dictated, if we have ideal components, is dictated by the power dissipated in the transistor. And the way you can think about this easily is when the voltage and the current, when the instantaneous product of those is non-zero, we have some dissipation in the device. And as you can see, the collector current and the collector voltage have a strong overlap in the class E. And that's, we end up, if we calculate our ideal efficiency, it's going to only be 50%. But we do have a very linear operation, which actually is going to be key for some of the stuff I talk about later. The Class B operation is we're operating with exactly the same circuit. What we're going to do is we're going to take the input here and we're going to bias it a little lower so that the transistor is only on for part of the cycle. So you can see the Class A kind of shape. And in the Class B, we're just turning the transistor on for a partial cycle. And you're saying, okay, well, how does that really benefit us? Well, once again, we're looking at the dissipation in the device. And if we take the product of this collector current and this drain voltage, we notice, collector voltage. When the collector voltage is high, there's no current. So we sort of get away from this area of high dissipation here. We still have an overlap in some dissipation. And if you go through all the calculations, the theoretical efficiency is 78.5%. So that's much better than the Class A. We get some nonlinearity here, as you can see, with this current waveform, but we stick a filter out in the output, and that helps filter all that out for us. Now, the Class E is a very popular topology, and the Class E is a bit more complicated to analyze. We've got a CMOS switch here. Typically, we do these with CMOS, but we can also do them with a SiGe transistor. We've got we're going to replace this transistor in thinking with a switch. The load consists of a drain capacitance. So this is actually the parasitic capacitance of the transistor and an additional capacitance that we put on the transistor. There's a bias choke, L1, and then there's also a filter here of C2 and L2. And one of the benefits of the Class E is that in its dynamics, it takes into account this drain capacitance. So this natural parasitic capacitance of the MOSFET gets embedded into our algorithm so that we can actually resonate that out. So a Class E does a resonance of the drain voltage, and typically people have a quasi-AC analysis for this, but then end up in the time domain tuning it, because really what we're trying to do is shape the waveform on the drain, and I'll show you here on the right where that is. So to look at this picture, this is the switch current, this is the capacitor current, and here is the drain voltage. And what you can see here is that when the switch current is 0, we have a positive drain voltage, our magnitude on the drain voltage. And when we have switch current flowing through, we have 0 volts across the transistor. So if you look at the product of these two, you're going to end up with an ideal efficiency of 100%. The trick here is to get this transition between the drain voltage getting near 0 and turning on the switch. And that's a bit of a complicated tuning technique to try to get this to work. Now, I said theoretically it's 100% efficient. What do we actually get? There's a nice paper here that allows us to easily kind of rule of thumb calculation based on the frequency, the on resistance of the transistor, and the drain capacitor, figure out some efficiencies. And what I've plotted here is, here's frequency, here's drain efficiency, and we see that for a 45 nanometer process with an FT of about 250 gigahertz, our theoretical efficiency is 65%. So this is ideal passives. Everything's perfect in the circuit. We're just looking at the technology. Around 65 is what we'd expect maximum. In addition to efficiency, one of the things that we're looking for is high output power. And it turns out that high output power puts another set of constraints on your power amplifier. And the output power is related to the basically output voltage and the output current. So if we want higher output power, we should have higher output current or higher output voltage, and both are a problem. The supply voltage limits how high the voltage can go. You may have heard a lot of work on gallium nitride. Is a very new popular technique for high power amplifiers. The reason is it can handle a very, very high supply voltage. CMOS, we're limited to just a few volts. For current, we're limited by current for two ways. One is device size, and the other one is I remember I told you that the drain source capacitance of the FET is used in the algorithm to calculate efficiency and to tune our waveforms. If you want more current, you want your switch to be bigger. If you make it bigger, you end up with a larger drain capacitance. And it turns out that you move out of the optimal design space. So we're limited there by our drain capacitance. And the other thing that's a little bit less intuitive is if you've got a fixed voltage, the only way to increase power is to increase the output current. Well, if I've got voltage and I keep on increasing my current, the output impedance gets smaller and smaller and smaller. And that becomes a real issue because I've got to now take an output impedance that might be an ohm and transform that to 50 ohms. And the networks that do that tend to be quite lossy, particularly if we're pumping a lot of power through them. So at 45 gigahertz, just kind of give you an example, we found that about 250 milliwatts is about the maximum power that we can get out of a CMOS PA in 45 nanometer technology. And this is based upon the trade-offs I just talked about, current and voltage. If we want to do 4 watts, we're going to end up needing at least 16 power amplifiers combined together. So we've got challenges both for efficiency and then also in trying to create high power. So I talked before about power added efficiency. I just want to define that because we're going to use this in our optimization algorithm. Power added efficiency is the output power minus the input power divided by the DC. Basically, how much additional power did I give divided by the DC current I'm using. The collector efficiency is just the output power divided by the DC power. So I'm not including anything I put into the device, which, by the way, for these PAs can be significant. We can put 10, 20, 30 milliwatts just driving the PA. The gain of the PA we're defining just as P out over P in. And if I combine these things, I can rewrite PAE in the following form, where I have basically drain efficiency times 1 minus 1 over A, where A is the gain. And this is what I'm going to use for my optimization algorithm going forward. So here are some simulation kind of design of experiments to see what we should do to create a PA in SiGe bipolar. We started with SiGe bipolar. We'll talk about CMOS in a second. So what I've done is I've plotted collector efficiency versus output power. So this is eta, as I mentioned before. And I did a class AB amplifier. So this is kind of a morphed version of the class A and B. I've done a class B by itself, and I've done a class E. Now, as I sort of described before, class E does have the highest collector efficiency, but class B is pretty high itself at high power. So class E and B aren't so bad in this technology. A has a much lower drain efficiency. When we go look at gain, however, here's gain here on this axis and output power, what we notice is that class E has the lowest gain. Why is this? Well, a bipolar makes a pretty poor switch. So it takes a lot of power to drive this bipolar transistor on and off, and therefore we end up with a large P-in and a low gain. Class B is decent. Class A, though, has the highest gain. And this makes sense, because in Class A, we're biasing the transistor so it's always on. We're getting the maximum gain out of the device we can. If we want to put this together in our PAE equation, we find out for power added efficiency that the additional gain and collector efficiency of the Class B actually wins out over the Class E and the Class AB. So we chose to go with the Class B in the SiGe bipolar based upon these trade-offs. So we went and built a power amplifier. It consists of 2 stages. The first stage uses a Class A amplifier. The reason we did this is we were looking for a high gain, and as we saw, Class A gives us a very high gain. Low efficiency, but we're not looking for a lot of power out of this. We're looking to amplify our signal. The cascode here increases the output gain. And then for the second stage, we're using a Class B. And we're using the Class B to get a high drain efficiency. And I should mention here that there's no cascode. The reason why we don't have a cascode is in this particular architecture, we're going to look at modulating the supply voltage. And if you move the supply voltage too low with the cascode in here, you'd end up running out of headroom. So this was our approach. Basically, first stage optimizes A, second stage optimizes eta. So how do we do? I guess before I get there, let me talk a little bit about some of the RF components. All of the large inductors that are here were done with a spiral inductor. All of the smaller inductors were done with a transmission line or strip line inductors. These patterns on the bottom are simply patterns in the substrate to reduce eddy current losses to give us a higher Q. We've got about a Q of 30 in these inductors and about a 10 to 25 out of these inductors. So here's a chip diagram where you can see here's the first stage transistors, here's the second stage transistors, here are all of our biasing chokes, and then also our impedance matching inductors that we saw on the previous slide. Here's our basic test setup. I show this to let you know that there's a lot of connectors that we have to actually de-embed in order to get an actual accurate result for our amplifier. So here are the results. I've got 2 things here on the left. One is power out, which is blue. The other one is gain, which is red. And here's input power. And what we can see is that through most of the region, we have a pretty flat gain, which is pretty good. For high PAE, we need high gain. We'd also like it flat. The output power gets up pretty high, where we end up with an output power peaking at about 17 dBm. So that's roughly around 50 milliwatts. The PAE starts low because we have a lot of DC current but no output power. And up here at the peak, we end up at about 26%, which actually is very good if you look at the original slide I showed you of where state-of-the-art silicon was. Here's just a breakdown of the power, and what we can see is the driver stage. The first stage is pretty much low power, and the output stage takes all of our power for our DC consumption. So at 45 gigahertz, we get a peak power added efficiency of 26%. We have a saturated output power of 17.5 dBm. I told you we wanted to modulate the supply, so we took the supply and we modulated it from 1.3 to 2.5 volts. So this is over a volt variation. And here's the power added efficiency for all of these supply voltages were all above the 20% power added efficiency. So this was pretty significant over a 6.5 dB variation in output power. We have still over 20%. And we ran at 2.5 volts. We ran the power amplifier for 48 hours and didn't see any degradation in the devices. Just to kind of put this in perspective, here's a chart, but here's the data. Here's this 20% line, and we beat this by about 25%. So when we published this work, this was close to the world record for power added efficiency from about 20 gigahertz up to a couple hundred gigahertz. So this was some pretty good work in efficiency numbers. What I just showed you was a single power amplifier, which is shown right here. We've moved on to, on the same die, we've got a 16-way, and we have an 8-way. We started testing in November. It turns out that it's very challenging to get these PAs integrated with an off-chip combiner. I'll talk a little bit about our combiners. The integration of that's still later testing of this, so we're hoping to get some test data on the 8 and the 16-way pretty soon. Now, let's go back and look at a CMOS PA. I'm going to use the same charts I did before of drain efficiency, gain, power added efficiency. I've plotted drain efficiency versus output power. Class E is still the clear winner. That makes sense. If I go over to gain, however, all of a sudden the Class E is also winning in gain. Why is this? Well, it takes very little energy to drive that 45 nanometer gate, and we end up with a very high gain at reasonable power. So if you've got the higher collector efficiency, the highest gain, it's not surprisingly that Class E wins out for the higher power added efficiency. And so that's what we went with for a 45 nanometer CMOS PA. This is our topology. It's a 3-stage. Our target goal was 262 milliwatts per stage. It contains 3 different stages. The first one is a pre-driver chain. This is just simply some digital inverters that come for almost free in the 45 nanometer process, both size and efficiency-wise. The second stage is like a Class D driver. This node is basically switched high and switched low to drive the final output stage. We use these cascodes to allow for a high voltage swing. And the reason we're going to have high voltage here is this inductor and this LC tank here are resonating out the input capacitor of this FET. And if you've worked with any resonant tanks, we can find that the voltage often will exceed our initial drive voltage. So we get pretty high voltage here. We want a cascode not to break down our devices. And as I mentioned before, this network here is to resonate out the gate-to-source capacitance. For those of you that aren't RF designers, if I've got a large capacitor, I can place it in series or parallel with an inductor. At a specific frequency, they'll cancel. And it's as if the capacitance wasn't there. And that's exactly what we're trying to do here at 45 gigahertz. The last stage is the Class E output stage. Here's our Class E switch. Here's a cascode. The cascode is there so that you can get a higher voltage on the output. For a Class E, this node will go about 2.5 times the supply voltage. So this node is going to go up to about 4 or 5 volts. So we really need something to help us protect our lower FET from high voltage. We're doing a self-bias cascode. I'll talk to you in a little bit about what's important about that and some ideas we have on modifying that. One thing that is not our original idea, but it's very clever and very needed, is when you're driving a cascode, you've got a gate-to-source capacitance here. And so this FET has to drive that capacitance. And that capacitance in a high output power amplifier is pretty significant. And it turns out that you can get about a 4 or 5% efficiency boost by putting a resonant circuit here to resonate out that gate-to-source capacitance. So this is something that typically for power amplifiers we wouldn't do, but it really does bring a big benefit here. So this is a little bit of an eye chart here, but we've got some tables to give you data if you want it. You can look on the right. Here's a cartoon of our drivers and our final output stage. And this is just a Pareto chart. For those of you that aren't familiar, I plotted power loss here and then the different individual stages. And basically, I orient the order of them so that the biggest offenders are here on the left. And it's not surprising. The biggest offenders are M1 and M2, which are the drive and the Cascode device. The simulated power added efficiency was 52%. This is very idealistic, but still it's a very good number. 65 was the theoretical maximum, so this is well on target from a simulation standpoint. We then wanted to look a little bit closer at the dissipation in M1 and M2. And what I've plotted here is the drain current, which is the same for both, and the drain voltage. And then I plotted the power dissipation in M1 and M2. This is basically looking at the product of these two. By the way, you can see pretty clear that the drain voltage doesn't get to 0. This is 0. And for the drain current doesn't really go to 0 either, but it's pretty close. So this is as well tuned as we could get it. And we end up with some dissipation when the transistors are on and when they're off, and we've just integrated this over here to give you some numbers. And we'll use those on the next slide because we wanted to see if we can improve the power dissipation in these two devices. So what we did is this was the self-bias Cascode. So here's your output. Basically, you've got a little RC filter here. Basically generates this voltage based on the output. And that gives you a DC voltage on M2. Really, however, we'd like M2 to be completely on when M1 is driving. And when M1 is off, we'd like M2 to be an isolator. So we'd like it to be completely off. And we can help this turn more on and more off by actively driving it. So we proposed a different Cascode drive that actively, synchronously turns on M2 on and off with M1 to see if we can improve the efficiency. Now I'm showing here on the left the exact same chart you showed before. The thing to pay attention to is down here on the bottom, the numbers. We did the same calculation for the new proposed Cascode drive. And what you can see is on the on state, we've got a little bit of improvement. In the off state, we have a significant improvement. It's not quite 50%, but we've got a big improvement in energy loss due to that Cascode drive. So with all of that put together, we end up moving the power added efficiency from 52 to 56% in simulation. We have those chips back now. We're running into the same integration with our combiner fabrication problem, and we're hoping to test those in the next month or so. We've done the die I showed you with the 16-way PA. And I want to mention this work is being done in collaboration with a team at MIT. Vladimir Stodanovich at MIT is doing a whole bunch of the, if you remember at the first slide, I said we're going to take a signal, we're going to decompose it to drive two PAs. He's doing all of the nonlinear modeling and compensation to figure out what we drive the PAs with. Joel Dawson's group is working on the modulator, which converts the digital signals to the RF band, and then my group is working on all the power amplifier work that I just discussed. And here's just a summary of what we're hoping to do for this. Now, I mentioned a lot, yes? So thermal, initially with the 16-way SIGI, we hoped that we'd be able to use the PC board and turn it on briefly in a thermal time constant. For the 16-way, we've actually designed a copper heatsink with CPU fans to actually bond down onto the die. The way it'll be done is the die will be flip chip bonded on a substrate, and then we'll bring down a heatsink for it. But we don't expect the CMOS PA to work without a heatsink on it. It's just going to be way, 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 way too hot. The SIGI, we were a little bit naive when we first designed the board because it's bonded this way and then just bond wired out. So the board is the only heatsink that we have. So it is a real issue for us. Once again, we're just trying to see what we can get peak. I don't expect us to operate for long periods of time at 4 watts if we get there. I've mentioned a couple times about power combining. I want to talk a little bit about some ideas and implementations we have from power combining. I like to show pictures from old papers because when you look at the picture, it sort of sets in your mind, wow, they must have done this a long, long, long time ago. It wasn't that long ago. It was just back in the 60s. Wilkinson proposed a combiner for combining multiple inputs into a single node. It's a very popular combiner. You may or may not be familiar with it, so I'm going to do a brief review because you won't understand what we've done unless you're familiar with the Wilkinson combiner. This is a two-way combiner. What we've got is 2 power amplifiers with an output impedance ZPA. And then we've got 2 quarter wavelength transmission lines, and this ZX1, which is a balance resistor. I'll explain all of this in detail in a second. And these two to connect together to deliver a combined output power to a load. I'll just mention in our work, the transmission line is a microstrip line, so we've got a gold shield, a thin dielectric, and a narrow trace on the top for the signal propagation. All right, so let's start with why a quarter wavelength. For those of you that love the Smith chart, here you go. There it is again. For those of you that have never seen it, here is a quick tutorial. Basically, the x-axis, if you will, shows the real impedance from very low to very high, with the center being 50. So we're actually able to map a very low to very high over a very compact range. The top and bottom quadrants, our hemispheres, are just showing where we have a complex impedance, where we either have a plus or negative reactance in our device. And the reason why we want a quarter wavelength is if we look at some output impedance and we want to impedance transform it to match the input impedance, we can build a transmission line with the characteristic impedance shown here, and you'll see this little convenient dashed circle I have. And by this being a quarter wavelength, we actually rotate from the real axis all the way around the signal, the source here, and we end up with an impedance over here. So the quarter wavelength is just magic, because we can go from a real to a real. We get a pi rotation in the Smith chart, and we end up being able to transform our impedances. Okay, so that's why quarter wavelength is key for our design. So let's take a look at how the Wilkinson works. We're going to talk about an even mode and an odd mode excitation. In even mode, the 2 input signals are in phase. If they're in phase, that means these 2 signals are the same. And if they're the same, no current's going to flow through ZX1, so we can just ignore it. And now if we look at this, I basically have 2 input signals that are the same, 2 things in parallel. Why don't I just combine them into a single transmission line? I've divided the impedance by 2, and I can analyze my structure just like this, where now I can calculate what my transmission line impedance should be based upon ZPA and ZL. Okay, so that's our even mode combination. For odd mode, our 2 inputs are out of phase. We have 2 out-of-phase signals here. Because these are completely out of phase, we can actually think about the middle of this resistor and this output being a virtual ground. If we do that, we can actually just ignore the fact that the 2 are together, and we can write each circuit individually like this, where we have our balance resistor now. And then one key thing to ask is, what does a quarter wavelength line do when one end's a short? I showed you the rotation around, but what happens if one end's a short? It turns out a quarter wavelength will take that short and make it into an open. And if that's the case, we can just ignore these 2, and we end up with the following. And all we need to do now is impedance match this to this in order to have isolation for all of our odd mode components. Okay? So that's how the Wilkinson works. Now, one of the challenges in actually trying to build these are, this is a picture of a 16-way die. We have all these PAs nice compactly put together. However, the actual pitch of the PAs is very narrow. And a quarter wavelength of, on the substrate we're looking at is on the order of 600 to 800 microns. And so this is a significant fraction of wavelength. So the idea that we're going to put all these quarter wavelength transformers in this tight area is a big problem. And also, because we're using microstrip lines, we have a narrow impedance range. We can make a transmission line from about 15 to about 90 ohms. And that presents a significant constraint on what we can build. And we came up with a solution that sort of takes all of these constraints and comes out with a very compact combiner. So what did Wilkinson originally do? He actually proposed a radial. If we wanted to do 8 PAs, his thing would be take 8 quarter wavelength transformers, put them all in parallel. Here's our load. And if our PA impedance is 10 ohms, we can use our equation and calculate what each transmission line should be. So this is just 8 in parallel converting. This was a radio technique. You can think about this as just taking everything into a single 10 PAs, 8 PAs in parallel give us, if it's 10 ohms impedance divided by 8 gives us 1.25. With a load impedance of 50, and we can calculate what our transmission line looks like that. These are some of the pictures. The radio combiner is fabulous if you have discrete power amplifiers and you're going to take your output signal off the center, because the radial symmetry makes layout really easy. If we've got a bank of PAs here and a bank of PAs here, it's not so convenient to use a radio combiner to combine everything. If you actually try to lay it out in a planar configuration, this is what you get. And what you can notice is to make this guy touch here, it's quite a bit longer than a quarter wavelength. And you end up with a significant variation in the current flow because basically each one is not a perfect quarter wavelength. When we simulate the efficiency, this is going to look a little weird. This is S1X, so 2, 1, 3, 1, 4, 1, 5, 1, where each one represents the 1 through 8 inputs. If we have a divide by 8, the ideal number would be minus 9.03. So that's our target for an 8-way divide. And you can see that we've got a minus 9.2, a minus 9.8. This line here represents the dissipation loss, which is right around minus 9.5. And the splitting here is actually the mismatch. So the reason why we're getting less power, less loss, and more loss here has to do with the fact that we have a poor impedance matching due to that, the fact that the quarter wavelength can't wrap around very easily. So one of the ways around this is to do a corporate combiner. And basically what we're going to do is take the 2-way combiner and just cascade it. We can run through the design for a power amplifier of 10 ohms on the output impedance. I can select 71 ohms for this transmission line. My 50 now becomes 50. I can now take this 50, translate it back using a 71. I get 50 here, and then I'm going to take my 50 to 10 and use a 32 ohm, and there I'm done. The problem with this is I'm now 3 quarter wavelengths long. So I talked to you before, we don't have a lot of room, and now I've just made a structure that is 3 quarter wavelengths long. But it's easy to lay out because it's already sort of in a network. So we like this idea, and we wanted to build something that was a little bit more like the radio combiner. This is a simulation of the corporate. You can notice here that the total loss is about the same, about minus 9.5, but the splitting due to mismatch is much smaller. So the corporate does a fantastic job for match, but we've got a lot of loss from it being so large. So my student came up with sort of an idea to get the best of both worlds, and this slide should sort of show you how to think about it. Let's think about a quarter wavelength transmission line, and we can arbitrarily go in and pick a segment, let's say the center segment, and represent it as 2 parallel transmission lines. And I can take this segment and represent it as 4 parallel transmission lines. And basically, if the parallel combination of these equals the same impedance, the parallel of these equals this impedance, I basically have an equivalent circuit for this. So this is basically just decomposing this transmission line to here. We're ignoring the fact of these little interconnects for right now. But you can sort of understand we're just doing this in parallel. Well, if you look at this, I just want to point out that the length of each of these sections add up to be exactly a quarter wavelength because we still need this reel-to-reel impedance transformation. It doesn't take very much to say, okay, well, what if I just put individual load resistors on here? Now it looks like I've got a 4-to-1 combiner that works pretty nice, and it's only a quarter wavelength long. You can actually take this and extend it to 8 ways, where we're going back to our original design. If you remember, where we collapsed everything to a single transmission line, we had an output impedance of 10 divided by 8 of 1.25, or output load of 50. And we're actually able to go through and design this with each transmission line. If we calculate all of the characteristic impedances, here's what they are. You just notice 15.6 in parallel with 2 is 7.8, parallel with 4. And the actual lengths of these is really arbitrary. You just design them how you like in layout. One question happens, well, if this is not exactly a quarter wavelength, what happened to this perfect pi rotation? I'm not going from reel to reel. And it's true, the input impedance looking in here is going to now have a complex component. In here is also going to have a complex component. And one of the repercussions of that is the fact that our balance resistors now are complex. In the Wilkinson combiner, if your sources are real and your loads are real, your balance resistors are real. In this configuration, your balance resistors would need to be complex, which is not trivial to implement. However, if you're looking at combining equal amplitude in phase power amplifiers, we're more concerned about getting the most out of the even mode. As I mentioned before, we're pretty constrained by the the impedance range that we can do for the transmission lines. If you go back here, you notice we're starting to get a pretty wide variation in impedances that we need. It turns out that this is sort of a cartoon. If you go try to make this, your transmission lines get really big. So here's a 400 micron wide transmission line. Lambda over 4, I apologize, it's 1,200 microns in this case. If you go and design this, it looks pretty hideous. And so you end up with a ton of current crowding and a very large splitting in trying to realize this design. And an easy way out is to try to just do a compromise where we do the same quarter wavelength compact combiner I just described and then we do a quarter wavelength transformer on the output. I won't go through all the design numbers here, but you end up with something that looks like this, and we have a much better balance in size and in loss. And here we are now with a much smaller mismatch, our impedance mismatch there, in a lambda over 2 footprint. So we've got a much more compact combiner with a lower mismatch and loss. And so we're off making those to do our combinations. And so this is sort of a summary of the work that we're doing of the 16-way, the SIGI with the SIGI combiner, and then also the CMOS with the CMOS combiner. These kind of some specs that we're at right now. So that's the work that we're doing on power amplifiers. We're really trying to focus on efficiency and power combining to see what we can get out of these. So I'm going to go to a different topic in the next part of my slides. And this is dealing with speed and uncertainty. And this is really looking at jitter in high-speed ADCs. And sort of the theme between all of these is we're looking at the physical limitations of achieving high performance. The motivation here is on top is sort of a narrowband approach for conversion, where I've got an antenna, a low-noise amplifier, I down-convert it. You get your homodyne or your superheterodyne transceivers, and I end up getting an ADC at the end with a very narrowband signal. Ideally, we'd like to take our antenna, have an amplifier, maybe a little filtering, and do direct conversion. We may not do the entire band from 0 to 100 gigahertz, but if we want to look across a wide spectrum, it would be nice to have an ADC that could look at a wide range. And so that's our motivation here. So what do ADCs do? In general, they create a digital representation of an analog signal. So what we're trying to do is create from the signal level, we want to create time pairs of a voltage and the time. This requires both timing and level. And timing I have in italics here because this is what we're going to focus on. Here's sort of a canonical architecture for an ADC. I've got my signal. I'm going to filter it. I'll sample it. I'll have my quantizer. This is where I convert from analog into digital. A codifier, which will help me put it out in a form that's easy for me to understand. I'm going to talk about and focus right now on samplers and quantizers. So what are the limitations for data conversion? The first is quantization error. And quantization error is simply I have an analog signal coming in, and I want to put it in bins. Okay, so these are the bins. These solid lines are the bins I want. And when I place it in a bin, the signal may be epsilon away from the actual bin that I put it in. So whatever bin I choose, there's an error dependent upon what the signal is. And if I calculate that error, it turns out that the power spectrum for that is related to the bin size, this delta here, divided by 12 if you go through some of the math where you can calculate the bin size from your full scale divided by 2 to the n. And the signal-to-noise ratio can be, we're going to use this commonly, is just 6 times n, which is the number of bits, plus 1.78, which is a factor that we have. So it's sort of how we start to figure out what our signal-to-noise ratio is with this noise. If we want to look at KT over C, what is this? This is noise voltage on the sampling capacitor. So we've got this sampler and a capacitor, and we're going to have some thermal voltage noise on this. So we can imagine that gray is the actual signal, and then we're just going to have some random fluctuations on top. This is really important for high accuracy ADCs. The power of this noise is just KT over C. Like I said, this tends to be more of an issue for very high bit ADCs. The final error that I want to talk about is jitter. And jitter relates to random variation on the clock edge or clock period. And so what I've shown you here in gray, here's the signal. In gray is when we would have liked to have sampled the signal. Here is a standard deviation plot of my clock edge. And if I happen to sample prior to when I wanted to, I have an effective error. I think I sampled at this time, but I sampled at that time. And so the voltage I read has an error off what I wanted to sample. And if you go and calculate the power due to this, you end up with something that's related to the frequency and also the standard deviation or the jitter of your timing clock. And your signal-to-noise ratio can be written this way, where the key thing I want to point out here is omega's in here. So as you crank up the frequency for your ADC, this term becomes more and more dominant. In fact, if we do a quick calculation, this is a 30 gigasample 6-bit ADC. I have put in my jitter noise. I have put in my quantization noise. I put in my KT over C noise. I get my signal to noise. I can calculate an effective number of bits. This is basically how good is my ADC effectively by placing this SNR in here and calculating that out. Here's a plot. Here's the effective number of bits. Here's clock jitter. And what we can see is to get 6 bits, we need a clock jitter that's below 0.2 picoseconds. Okay? So jitter here is the dominant degradation of our effective number of bits. This is well put. There's actually a Walden plot, which is well known. A friend and colleague, Boris Merman at Stanford, has done an updated plot based upon the latest circuits conferences, so calling this the Merman plot. This is the bandwidth of the ADC. This is signal to noise ratio here. I've put in the number of bits so you can sort of see where everything correlates. And what you notice is everybody is bang right against this jitter line. So this really is a fundamental limit, where here's the 1 picoseconds of jitter, here's 100 femtoseconds of jitter. And so what we're trying to do is investigate exactly what are the causes of jitter and what can we do to mitigate those effects. In both high speed sort of is relative. Up here you might be talking about a 40 gigasample or 60 gigasample ADC. Down here you might be talking about a couple hundred megahertz. But a couple hundred megahertz at 14 bits is a very high performance ADC. So I've told you jitter is the limitation for high speed. Why are the circuits not a problem for us? And the answer is that we can alleviate our need for an individual ADC to run at 40 gigasamples or 80 gigasamples by doing interleaving. And what we do is we take all of the speed complexity and we throw it into the track and hold at the front. And these circuits then can operate at a much lower frequency. So typically, these might operate sub 4 gigahertz, and our track and hold might be operating at 40 gigasamples. All of our issues with jitter, however, have not gone away. They're just piled right into this track and hold, but the circuit side is a little bit relaxed. So what is the problem in trying to deliver high-quality clocks for an interleaved architecture? There's 3 problems, really. One is generating a clock with a low enough jitter. The second one is getting that clock to your track and hold on the chip. And the third one is making sure that your sampler is using that clock in the best way. And also, we'll talk about if your clock gets degraded as it propagates there, that'll affect your signal-to-noise ratio in sampling. And so I'll talk about each of these quickly. For low jitter electrical clocks, just to kind of put you things in perspective, just remember, we want 200 femtoseconds. Ring oscillators are a few picoseconds of jitter. LC oscillators are right around 1. If you have a PLL with a crystal clock, the added jitter is somewhere in the 200 to 400 femtoseconds. You can buy a commercial microwave synthesizer, and depending upon your bandwidth, and I'll explain that in a second, you can get anywhere between 50 to a couple hundred femtoseconds of jitter. And why does bandwidth matter? Well, here's a phase noise plot of an oscillator. We calculate jitter by integrating underneath the curve from some frequency to another frequency. So you have to define your bandwidth from an oscillator in order to integrate and figure out what your jitter is. So you can do some specmanship. If somebody tells you the jitter of an oscillator, you really have to know what the bandwidth is. Optical clocks are fantastic. They do sub 50 femtoseconds of jitter. Franz Kertner and his group at MIT have shown a 7-bit ENOB at 40 gigasamples per second in an all-optical ADC. It's a tabletop about the size of a pool table, but they're able to show excellent performance. All right, so what's the problem with clock distribution? Generally, your input clock is a sine wave, and you're going to use inverter chains to basically buffer it up. Why do you need to buffer it? 1, you've got loss and distribution, and 2, you're going to drive a very big FET at the end for the track and hold. The estimated added jitter per inverter is anywhere between 1 to 20 femtoseconds. So if we've got, I just threw a number out here, 4 to 20 inverters between the clock source and the clock delay, we end up adding significant jitter just through the clock delivery. Another issue is in interleaved design, sometimes we want to deliver the clock to each ADC branch, and the delay to each is not known until we build the device. And so what we want to do is, you can see that my clocks don't happen exactly where I'd want. So the gray lines is where I would, the arrows here where they're actually happening on a 4-clock system. And what we typically do is put a variable delay in to realign these things. These are some degradations in the signal. This is just a spectrum output showing additional tones caused by mismatched clocks. So what you'd like to do is just adjust these. How do you adjust them? Well, you can do them by adding in coarse delays, adding a lot of logic gates or taking them out. You can also fine-tune delays by, this is one design where you have a DAC that's doing sort of a periodic loading of capacitors on an inverter. The problem with both of these approaches is each one's adding jitter. So while we're correcting for delay, we're adding jitter by adding more digital components in the way. The final thing I wanted to talk about was I talked about clock degradation. When your clock finally gets to your sampler to drive your track and hold or your sampling switch, your switch is really going from a low impedance state or on to a high impedance state when it's off. And there is a transition, and if that transition is significant, the impedance is changing quite a bit. And so if you have a high frequency component of your signal, it's going to get attenuated quite a bit while this transition in bandwidth is happening. If you have a low frequency, it's not going to get attenuated. And so you get a nonlinearity in your filter in that high frequencies are being attenuated more than low, and it's happening based upon the right of your switch. Why are we caring? Well, typically, right after the switch stops is exactly what we want as a signal. So everything that happens right before it has a significant effect. And you can go and calculate what this modulation does in terms of a degradation, and it's very similar to clock skew in adding additional tones. So what are we doing to address these issues? The first thing we're looking at is jitter in the distribution tree and buffering and correcting for clock skew. We've got a chip back now measuring where we're trying to actually quantify the different delay techniques of using current-starved inverters as a delay line, capacitive loaded lines as an inverter, and also a lot of the work that I've done in the past has been with nonlinear transmission lines. And this is an inductor capacitor lattice. If these are linear capacitors, it's electrically equivalent to a regular transmission like a microstrip. We can think about a low nonlinear regime where we're just changing this capacitor just a little bit. So the change in capacitance is very small. And basically what it does is it modulates the velocity of the wave. So we're creating a delay, basically modifying C. For a microstrip line, this would be the same as moving it closer or farther away from the substrate. So we're looking to see what the jitter added from this is going to be. Here's a dive photo of the nonlinear transmission lines and the delay lines. And right now, we're just beginning testing. Testing's a little complicated because it's not like you can just hook this right up to your VNA and say, give me the jitter. First of all, the jitter added by these are probably on the order of 20 to 60 femtoseconds. And also, there isn't a two-port jitter measurement system that's very accurate. So what we're doing is we're using something that's commonly used. It's a discriminator double balanced mixer approach. And this is how your VNA or your PSA and all these instruments actually do their noise calibration calculations. We're going to take a reference oscillator. We split it into two signals. We place one as the input to our device center test. This might be a transmission line or delay line. We take the output. We put it into a mixer. Here, we've taken the same input signal, phase shifted it. We're going to input it in the mixer. And then we down convert. We self-mix this down, and we look at the noise spectrum of this. And it turns out that if our phase is 90 degrees, we end up with our output DC value being related to phi of t, where phi of t is the phase noise or jitter. If we have 180 degrees of phase shift, we end up with our output being related to the two amplitudes. We can actually measure the amplitude noise added by this device center test. This is a very accurate way to measure phase noise. This is what NIST does for a lot of their calibration standards. So we're building that right now to build the previous test structure. All right, let's talk about clock degradation a little bit. I talked before about this nonlinear transmission line. If you operate this in a high nonlinear region, what does that mean? That means that my signal basically is causing a dramatic change of capacitance here. It turns out that the equation gets quite a bit more complicated. And we have our nonlinearity from our varactors here, and we have dissipation due to loss. And it turns out that these two can compensate one another to form a shock wave. And the basic idea is I start with a soft edge, and as this edge propagates, it slowly sharpens up. Now, I don't get anything for free. The other edge of the clock starts at the same edge, and it gets softer or shallower as I go. So I can sharpen up one edge of a clock, and this helps me regenerate a high-quality, sharp clock signal at the track and hold. And that's what we're trying to do right now to see if we can actually achieve this. Another reason why this is important is timing jitter is generally found from a voltage jitter divided by a slope. So in all of our inverters, if we can drive them with higher and higher slopes, we'll end up getting less added jitter from each. That's another benefit to having sharper edges. Here's just a simulation where we're going from a 20 picosecond rise edge to about a 1 picosecond rise edge with these transmission lines. All right, the last part of my talk is going to be talking about an actual ADC and jitter sensitivity. And what we're doing, as I talked to you before, our target are these large high-speed ADCs. But since we're interleaving, we only need to focus on a single channel. And so what we're going to do is focus on jitter and noise in a single channel. We're going to focus on a 5 gigahertz Nyquist. What does that mean? It means we're going to try to sample at 10 gigahertz, hopefully being able to do a 5 gigahertz signal. The target's 40 gigahertz subsampling topologies. We're doing this in 45 nanometer SOI because digital calibration is quite easy to do, and integration is also pretty easy. So we're focusing on the technologies. We think it's got a lot of legs going forward. So here's a cartoon of what we're looking at. I'm going to walk you through it because it'll sort of show you the complexity of a switch cap ADC and also some of the ways that we can get the jitter sensitivity to be reduced. So this part is our sampler. It's a track and hold. And the second part is a quantizer. I'm going to run you through this step by step. What we're going to do here is called a bottom plate sampler. Bottom plate because I'm not using this switch to define my time instant. I'm going to use this switch, and it's attached to the bottom of the capacitor. All of our amplifiers are open loop. Why are they open loop? Because this is going to make us go very fast. And then at the end, for speed, we're also using multiple regenerative latches to increase our speed. So here's a single channel. I'm going to just walk you through. We're going to start with the switch open. We're going to have this switch closed. You don't need to pay that much attention to this. The red line will just walk across here as we go. We're going to sample the input voltage onto this capacitor. The bandwidth, this doesn't come out very well, the bandwidth is determined by the resistance of these two switches and this capacitor. Depending upon sizing of these switches, we can get between 50 and almost 300 gigahertz on chip bandwidth. This is extremely optimistic, but at least the technology, has that potential. So we've loaded the voltage onto the capacitor. Now we open this up, and the voltage is just sitting floating here on this capacitor. This node, while we weren't watching, was loaded up with the previous cycle with VREF. So we've got VREF on this capacitor. This is floating. I'm going to open this up and close this switch. And now I've got VREF. This node here is VIN plus VREF. Okay. And then what I do is I close this switch. It dumps charge onto this node. I've now got VN over 2 minus VREF. And I'm going to compare that to an internal reference. This is basically looking at the difference between my reference. I amplify that. I'm then going to store that on a capacitor. And if I'm higher than my reference, my regenerative latch will go in one direction. If I'm below it, it'll go in the other direction. And I can create a 0 or 1 based upon the time domain output here. And so that's how the single channel works. What I wanted to show you, there's a lot of complexity in all of the switches going on and the timing. However, if we look at it, only this single edge, when the bottom plate sampler closed, has any relevance on our jitter sensitivity. All of the other clock edges are really can have quite a bit of jitter on them. We don't care as long as they don't overlap. So we've designed a circuit here that tries to minimize its sensitivity to jitter for these systems. We've run some simulations here. This is running at 5 gigasamples per second. We put a 1 gigahertz input signal. We get a simulated ENOB of 5. When we put in a Nyquist signal, or just below Nyquist at 2.4, we've got an ENOB of below 5, but still decent. It's a 6-bit target ADC. If you put this in comparison, these are all published data. Obviously, simulations can be way more optimistic, but we at least wanted the performance of the system to be competitive. We're sort of up in this range, and if you kind of blow this up for CMOS only, right now current CMOS is kind of stuck at about 2.5 gigasamples. We're trying to target. The simulation data was for 5. We're going to try to run this up to 7 or 8 gigasamples if we can. Those chips are back now, and we're working on testing those. This is a dive photo. This is the sampler. Here's the quantizer, and then the DAC. For those of you that do IC design and use our trusted DoD-supported foundries, we're running 6 to 8 months sometimes for our fab time. So every time I give this talk, we're a little behind, and so that's where we are with this. I have about 30 seconds left, and I just wanted to talk a little bit about what my group does, just to show you we do a lot of other cool stuff. My graduate work and PhD was in nonlinear electronics. I do work with soliton oscillators, mode-locked oscillators. A little bit of work with neural networks. Basically, nonlinearity is cool, and it's fun to play around with. You can see it manifesting in the ADC work. Another area that you may already know about is some interdisciplinary work that I'm doing with Professor Stansel and also Dr. Griffin at Disney Research. This is some non-line of sight positioning for American football. It's very cool. Professor Stansel can tell you lots about this. He's got cool videos to share. We're also doing some work sort of in this theme of magnetoquasistatics. We're doing some work in wireless power, which actually was inspired by Professor Stansel when he was at CMU. We've done a distributed system here where we've got a single transmitter in the center, and these are resonant coils that are delivering power over about 2 meters. These little guys right here are the loads, and we basically can show that we can use a repeater system to extend wireless power over a larger distance. And this initial application is for automotive based on our funding source. Some other systems work that's very cool. A colleague of mine, Seth Goldstein, came up with this idea of Claytronics. Claytronics is basically the idea that we're going to build virtual matter out of little teeny robots. And I got involved in trying to build the little teeny robots because they're cool. The idea is we use MEMS processing to take a 2D sheet of silicon. A guy actually at the Air Force came up with the IP for this work. By patterning metal on a very thin silicon substrate, we actually create stresses so that when you remove the backside, it rolls up into a tube. And here's an actual picture. And the idea is this is going to be a rolling robot. My student and I worked on a high voltage SOI CMOS die for control and actuation. And the basic idea here is we've got a substrate with 2 supply rails here. We've got a supply ring on either end. And we're going to capacitively couple power into the robot. And then we're going to use these actuation electrodes, which are controlled to our chip, to move it along the substrate. And the basic idea here is we've got basically half of a capacitor, and then we've got a full capacitor. By changing the charge, we'll actually get a net force that'll roll the robot. Here's a simulation with equal charge on all the electrodes. We bias the charge in one, and we can see an asymmetry that moves it forward. In case you believe that we were just thinking this might not work, here's a nice little video. Here we've put the electrodes on a substrate and put a solid tube, but you can see the capacitive actuation does actually work. So this is pretty cool. The final stuff I do is with several other groups at CMU, some work in nanofabrication. I run a program on tip-based nanomanufacturing. Here's our system. It's a STM, scanning tunneling microscopy-based system. My student wrote CMU. This is, I think, 15 nanometers high by about 30 nanometers wide. These individual dots are actually vacancies where a silicon atom is. So you're seeing the individual atoms or atom pairs along here. We wrote CMU. And the idea is we're taking a tip, an electron beam, basically to pattern a surface. And then also some collaborative work I have is on spin torque oscillators. This is a very cool area, but the long story short is you polarize all the electrons in your wire so that they have a net magnetization, and you can use that net magnetization to do a bunch of cool stuff. I'm working on frequency agile oscillators and coupled arrays in this area. All right, that's it. Thank you very much. Yes.
Quick question. Is the ADC you just mentioned Nyquist ADC or something?
It's a Nyquist ADC.
So you have a multi-bit quantization for each channel, or just single bit?
Each channel has 6 bits.
6 bits.
6 bits. And the idea is that I'm not using the parallelism to get me higher bits. I'm using it. Each channel itself has 6 bits. And then they just interleave. One takes the first second, the next one takes the next clock cycle, the next clock cycle.
So is the mismatch between each quantizer cause any problem?
Yes, yes. And I tried to emphasize at the beginning, the whole goal is to get a voltage time pair. And the problem is each one of my ADC channels does a good job of getting a voltage, but it's confused on what the time is due to jitter and due to the delay of the clock delivery.
Maybe, can I ask, if I have the right picture, if I'm thinking about the nonlinear transmission line, so I have a pulse going down like this, and the high intensity goes slower than the low intensity.
Yes.
So as it's going along, the tip sounds to tip
Yes.
over, making one side
Sharper, yes.
sharper. Got it.
That is exactly right. The problem is that it should eventually do that, and it stops because of dissipation.
Yeah.
So as you get sharper and sharper, your losses get higher, and then the system stops. It's very similar to traffic, a standard Berger's equation shockwave. Yes.
Very good talk. I really enjoyed it. And I have a question for you on your PAs.
Yes.
At the beginning of the. So when you, because you talked a little bit about the loading, so when you tested those PAs, did you test the CW or did you have the loading resistor? Did you change the testing way?
So the SIGGIs all have the load matching network on chip. So we did it discrete. So we just hooked 50 ohms up to it.
Okay, so you had the output. It was external 50 ohms.
It was external 50 ohms. On the CMOS die, we're actually using, remember I showed you that in the compact combiner you get a complex impedance if you don't make everything a quarter wavelength? We actually use that to create a complex conjugate to what the PA wants to see. So the combiner is actually also our output matching structure. And so that's a little tricky. We haven't started testing all those PAs yet, and it's going to take up some fine-tuning to get that.
But they were CW, so you just...
Everything is CW, yes.
You didn't try anything pulsed?
Anything what?
Pulsed.
Pulse? No. No, we didn't.
And they were room temperature?
Yes, yes, yes.
And another question on your nonlinear transmission lines. So most of them are actually non-passive because you have a tape.
Right. Well, the nonlinear transmission lines, they're all passive. And that's why they have a benefit.
Well, you have, I call non-passive because you have some transistors there. You have the one that I saw, there were some transistors.
I think you used some FET as
Yeah, you had some
variable.
Oh, I had a FET. Thank you.
Use them as variable capacitors or something.
No, this is where you realize that your explanation had this diagram here.
Yes.
The idea here is this is all passive, and this is my sampling transistor. This is my load, if you will.
So what was the technology?
Oh, the technology here was, to be fair, it was a FET where these two terminals were connected together. We're just using the gate drain capacitance.
But what kind of technology? Did you use a silicon?
Oh, it is integrated with the chipset. It's a 45 nanometer gate oxide silicon CMOS.
Or SOI? That's
SOI, yes.
there.
Yes. And it turns out that actually Ken O has done some good work to show that for absolute speed, the SOI is not the best. A CMOS varactor is not the fastest. The PN junction can go faster.
So when you tested it, you used just a pulse?
So with these, when you test them, you'd like to use a pulse, but generally you're trying to create something much faster than you can generate. And so you can just put in any square wave, and it'll sharpen that, or you can put a sine wave in. A lot of the work that people originally did was they put a sine wave in and translated that to a series of sharp pulses. Because whatever you put on the input, it'll turn into the waveform at once.
But you also don't have, it's not AC coupled.
What's that? Sorry?
When you tested, did you do AC coupled or?
Oh, it is AC coupled. One of the problems is this is very poorly impedance matched. You can't impedance match this properly. And so reflections happen all the time. So you basically just have to hope you're doing a cyclic system where you can ignore the reflection until the next pulse comes.
Okay, thanks very much. Let's thank our speaker a little more.